So in this video, we're going to be going over parallel circuits. This is a complementary video to the one we did previously with series circuits. We want to see voltage, what happens. We've got two batteries, but what is the voltage of the whole circuit? What does current look like in the circuit? I have multiple switches in here to turn on or off sections of the circuit. How does that look? And we have a voltmeter here to be able to measure it all. So what we can see here to start with, and on the right side I'm going to show how we can calculate what the current will be. Now of course we can see what the current is because these are accurate, but we can see how we would calculate it. So to start, let's just get the lay of the land, what's happening. We can see we've got two battery sources, each with the current leaving the battery, flowing through our bulbs or our resistors, whatever we want, and then flowing back to the batteries. We have two, you can see at the bottom, two 10-volt batteries. The resistance, I made 10 ohms. In each, I picked 10 and 10 because those are easy numbers to do on the fly instead of picking crazy numbers that I need a calculator and whatever for. Or to absolutely butcher mental math, which I don't want to do. So, one of the things we learned in series circuitry was that when you add multiple batteries together, you add up their voltages. So if these were added in series, which would look like this would have a total, and actually here, let me just quickly whip up a circuit. This would have a total of, oops, let me add a resistor in there. Okay, this would have, if each of these, well, each of these, its default is 9 ohms. We can measure what our voltage would be, and we measure 18 volts because both of them add together to get a total of 18 volts. Now, when we look at this series circuit, let me just disconnect that to make it stop moving. Sorry, I think I just said series. With parallel circuits, the voltage is not added together. We have the total voltage of one battery, and that's the voltage for the entire system. So we put our one lead on the side coming out of the batteries and the other on the opposite side after exiting, a resistor or a bulb or whatever. Notice it says the voltage is 10. I can put it here. The voltage is 10, 10, 10, 10, 10, 10, 10, 10, all the way, as long as I'm on one side of a battery and the other side of a battery, it'll measure 10. If I put this on the same side, notice the voltage is 0. The current is flowing here. There's nothing opposing it, no resistance. And so we're not detecting a potential difference because along this wire, there's no difference at all in the voltage. You can't tell a difference until you get to the other side. And that's why anywhere here, we measure 10 volts. Okay, so we've covered now, we've got two 10-volt batteries in a parallel circuit. The total voltage is the voltage of one of the batteries. Yes, you have two of them, great, but the total voltage of one is going to be used. Now, notice we have different currents. We've got two, we've got one. Well, what's the difference? So first of all, what we could do is let's calculate what we expect the total current to be. From our Ohm's law equation, we can rearrange this by dividing both sides by R, and we can calculate what current should be. Remember, voltage is 10 volts, and the resistance now, we need to divide by the total resistance. Now, what we had done with our series circuits was we added all the resistances together, in which case we would add 10 and we would add 10, so that would make 20 ohms, and so the resistance would be 20 ohms, and we would find, and this is incorrect, we would find that we would have 0.5 amps of current flowing. Of course, we see that that's not the case because we have to calculate our resistance differently. So in order to do that, we still have our same equation to calculate current, but when we're looking in parallel, this is when your total resistance equals 1 over your resistance 1 plus 1 over your resistance 2. And so 1 over resistance 1 is 1 over 10 plus 1 over 10 is resistance 2 equals 2 over 10. That's how you add fractions together. And 2 over 10 equals 1 over RT. I'm going to take the reciprocal of both sides, and I'm going to clear some of this off because now it's really messy. But I'm doing 1 divided by both sides, which will yield RT over 1, or just RT, equals 10 over 2. So our total resistance equals 5 ohms. Now we can go ahead and plug that 5 ohms resistance into our formula for calculating current equals our 10 volts divided by 5 ohms of resistance, and the current, lo and behold, equals 2 amps. Well, looking over here, we can see it as 2 amps. So yay, we've calculated it right. Now, the question you might ask is, well, hold on. Why do we have 2 of these that say 2 amps and 2 of these that say 1 amps, or 1 amp? And the reason is you need to look at what percentage of the current is flowing through that ammeter. Notice, as current is flowing back to the batteries, from both of these branches, all of the electricity is flowing through this. Now, after we get through this ammeter, notice it splits off. Half of it comes down through this battery, and half of it comes down through this battery. So the total current is 2 amps like we calculated. At the bottom here, we can see 1 amp of current because only half of the current is flowing through here, and the other half is flowing through here. Well, we can look at this one now and say, well, why is this one 2 amps? Well, again, the electricity is flowing through here and through here, all combining, and so all of the current is flowing through here. And we calculated the entire current is 2 amps. Great. Well, why is this one 1 amp? Well, the same reason that this one is 1 amp. At this point, half of the current gets divided up into this one, and half goes through this one. So if we had 2 amps of current here, it splits in half. We're left with 1 amp here and 1 amp through this one. So that's why we have these different amp readings, different current readings as we look throughout this. Now, the last thing, I think, unless I remember something when I finish this, to talk about is switches in parallel circuits. What we had before was when we had a switch in a series circuit, in a series circuit, added 2 bulbs. I know it's looking not great, but whatever. I'm sorry, let me cut that one off. There. When we had a switch in a series circuit, when it's open, no electricity flows, none of the bulbs can light up. When you close it, both bulbs light up. As soon as one bulb has a fuse, or the filament in the middle melts and breaks, no electricity can flow. Whether the circuit is open or closed, you have to replace the bulb in order for both lights to start working. That was how it worked here. Now, in a parallel circuit, which is what we use all over our homes, we can open or close the circuit to certain appliances. So if you only want one thing running at a time, you can do that by turning one thing on and leaving the other off. So notice we've still got electricity going to this light bulb, whether I let it flow to this one or not. Now, I mentioned I have 3 different switches here, so you can see this one still lets electricity flow. Notice the current flowing to this one is actually unaffected. It's still 1 amp the entire time. And we can calculate that because, well, if this part is closed, the total current is going to be, the total voltage is 10 volts, and the total resistance is going to be, well, we can calculate it. We're still, well, kind of parallel because of the 2 batteries, but there's only 1 branch for the electricity to flow through. So it would be 10 over 10 is 1. Now, I can open up this battery as well. Notice this one just cuts off the flow to this battery, but the current still flows. And at this point, we have a perfect series circuit. Just one path to follow the entire way around, whether this is opened or closed. Now notice what will happen with voltage. 10 volts here, and 10 volts here. We have the same voltage when we're open or closed because, again, you don't add the voltages together when they're in parallel. Now I can open up this switch. This switch, all the electricity from both batteries has to flow through this switch. If I open it, there's no way for the current to get from this side to this side. The entire system turns off. As soon as I flip that, then all of a sudden the current resumes again. So this is how switches work in a parallel circuit. If you were to consider one of your light bulbs burning out, boom, the electricity can't flow through the battery back to the other side. This is the only way on this thing I can simulate it, but it wouldn't be able to flow through here. Look at that, this light bulb still works. So this is why parallel circuitry is really nice, because if one burns out, fine, you can easily replace it, but the rest of the system will still work. Whereas, again, as I showed here, and it was in the previous video as well, when one bulb burns out, both bulbs are off. So looking at this, you actually have no idea which bulb is the problem because they're both turned off. Whereas in this one, of course, you can tell instantly, oh yeah, this bulb is burnt out. Or if this was the one, oh yeah, that bulb's clearly burnt out. So in this video, we learned how to measure current in a circuit. We're normally looking for, and I believe in this class, we're normally looking at calculating the total current. And the total current is calculated by using your voltage, which is just the volt of the battery. The batteries will be the same. The volt divided by the resistance. And we had to use that 1 over RT equals 1 over R1 formula, so on and so forth, to calculate the resistance, to plug it in, to solve for I, and that was the total current. We also learned how switches work to either restrict certain sections of the circuit, but why, even doing that, we can still get electricity flowing. And we saw how to measure voltage by connecting it on the one side of the batteries, going away from the batteries, and going on the other side back towards the batteries. To measure voltage, you can't put them both on the same side, or it'll detect 0 volts. 0 volts there as well.